Okay, so in this example, we are going to graph the logarithm, and we're actually going to graph this one over here. So f of x equals log base 3 of the quantity x minus 1 minus 2. But the instructions are to create a table for f of x equals log base 3 of x, and then we're going to actually translate to get this function over here. So if we're going to start with creating a table, we're going to start with this function, log base 3 of x. We've been referencing this as kind of like the parent function that then you transform. So to make a table for a logarithmic function, as a review, you're going to rewrite this in exponential form. So instead of y equals log base 3 of x, we can think of this as 3 to the y power equals x. This means that we're actually going to be filling in the y column first and then solving for x. That's just because of how this is set up. It's like y is your input variable in this case. So 3 to the negative second power is 1 over 3 squared, or 1/9. 3 to the negative first power would be 1 over 3 to the first power, or 1/3. Excuse me, 3 to the 0 power is 1. 3 to the first power is 3. And 3 squared would be 9. If we were to plot these points, we would still plot them like we always do, x comma y. Just because we plugged in y first and solved for x doesn't mean we change how we would actually graph it. But the reason that this is helpful to us is that now when we're looking at y equals log base 3 of the quantity x minus 1 minus 2, this is just going to be transformations placed onto this function. So for instance, the minus 1 inside the parentheses means that the original graph is going to move right 1. And then the minus 2 over here means that it's going to be moving down 2. So if you take a point and you move it right 1, that means that you're just taking your x coordinate and adding 1. So in our columns on our table, for our x values, we're going to want to add 1. And then moving a point down 2 just means that you're taking 2 away from whatever your y is. So we're going to subtract 2 from the y's over here in order to get the y column. So let's go ahead and do that. If we are adding 1 to all of our x's, that means we would have 1 and 1/9. But subtracting 2 from the y, we would have a point at negative 4. Adding 1 to x, we would have 1 and 1/3. But subtracting 2 here would be negative 3. Adding 1 would be 2, and subtracting 2 would go to negative 2. Adding 1 to 3 would be 4. Subtracting 2 from 1 is negative 1. And adding 1 to 9 would be the point 10, comma, subtracting 2 over here would be 0. So if we were to plot these points, still again, x comma y, so 1 and 1/9 would be about here. And then that's negative 4. So here's your first point there. 1 and 1/3, negative 3 would be about here. 2, negative 2. 4, negative 1. And 10, 0. So we can see that this graph would look something like this. Picturing how your original function is, log base 3 of x is something like this, where you have your asymptote at x equals 0 right here, right along that y-axis. So if we're moving right 1, it makes sense that our new asymptote moved right 1, and so our asymptote is now at x equals 1. On our original function, our domain went then from 0 to infinity, but since our graph has moved to the right one, it would make sense that our domain now, since it's still on the right side, goes from 1 to infinity, and then our range isn't going to be impacted. It will still be all real numbers. Now, I do want to point out just one more example. If you are asked to graph something that's the natural log, this is a situation where you're going to still have to use a calculator. Now, I would still recommend starting it the same way, meaning I would look at the parent function first. So the natural log of x, I would start with that and make our table here. Just remember the natural log of x is the same thing as log base e of x. So if we were to rewrite this in exponential form, we would say e to the y power equals x. So even if we were to plug in things like -2, -1, 0, 1, and 2, I'm not able to evaluate e to the second power, for instance, in my head. This is something that we're going to have to use a calculator for. So if you do use a calculator, I usually just round to a few decimal places. So e to the negative second power is 0.135. E to the negative first power is 0.368. E to the 0 power is 1. E to the first power is about 2.718. Again, these are all approximations. They're not exact answers. And E squared is about 7.389. So we can still do the same thing over here. When we have this negative in front of the x inside of parentheses, this means that we are going to be reflecting over the y-axis. And then the +1 outside means that then we are going to go up 1. So if we're going to make our table for this other function after the transformations, well, reflecting over the y-axis means that the first thing you're going to do is take the opposite of whatever your x is, right? Because if you had a point over here and then you reflect it over, instead of being 3 units to the right, it's 3 units to the left. So it's going to negate that x value. And then if we are moving up 1, that means that we are going to add 1 to our y. So all of our x's are going to become the opposites. So negative 0.135, negative 0.368, negative 1, negative 2.718, and negative 7.389. And then we're going to add 1 to all of the y's. So negative 1, 0, 1, 2, and 3. So plotting these points, we're going to see that at negative 0.135, negative 1, negative 0.3680, negative 1, 1, negative 2.7182, and then negative 7.389. So negative 1, 2, 3, 4, 5, 6, 7.389 is a little bit further, up 3. So this graph is going to look something like this, curving over this direction. Now, our original parent function, again, looks something like this, where your original asymptote was still at x equals 0. Well, reflecting it over the y-axis and moving up is not going to change where your asymptote is. So your asymptote is still going to be at x equals 0. But hopefully you can see that your domain does change. Moving it up and down isn't going to change it, but when you reflect it over the y-axis, our domain is now going to go from negative infinity up to 0 instead of 0 to infinity as it was originally. And then our range will still be all real numbers.